NMR spectroscopy, in essence, is another tool that we use to identify molecular structures. In the past, in the first year of chemistry, you've looked at infrared spectroscopy and mass spectroscopy. So let's just quickly revisit these particular areas. Okay, so infrared spectroscopy, as you can see over here, tells us essentially what a functional group is. For example, over here, we can remind ourselves that infrared spectroscopy will identify a carboxylic acid as a peak around the region of 3000, and it will be very broad. Similarly, the carbonyl peak will be around about 1720, and the carbon oxygen peak will be around about 1300. Now that's all well and good, but it does not give us any information about the structure of a molecule. For all we know, the carboxylic acid may be part of a 25 carbon chain long, or it might be just a simple methanoic acid. It gives us no indication about how many carbon atoms we've got. And for that purpose, we could actually jump and look towards mass spectroscopy. Now, within mass spectroscopy, we've got the molecular ion peak over here, so we know exactly how long the chain is, but then that doesn't necessarily give us any information about the functional groups or which fragment is sitting next to another fragment. All we know is that the fragments actually exist. So what do? Well, we use NMR spectroscopy. Now, if I just highlight this particular area over here, this is a typical output graph of how NMR looks like. And what NMR tells us is how many different types of environments I have. And I'm going to talk a lot more about environments later on. For now, all we have to worry about is the fact that the methyl group over here has this signal. The CH2 group has this signal over here, and the CH3 has this signal over here. How this signal corresponds to this, we will talk about in a few minutes. Let's look at exactly how one of these NMR machines looks like. And this is a typical setup. In actual fact, this was the real NMR room at Imperial College that I studied at during my postgraduate degree, and I've had the I would say privilege of using one of these machines. And why do I say I've had the privilege? Well, these machines are not cheap. The average cost these days for picking up an instrument of this kind would cost in excess of £2 million. And unfortunately, that's not the end of it all. It cost around about, I would say, 1, 2, 3, 4. You have a C double bond O, and the rest you have methyl groups. So let's put that there. Okay, so this is butanone. Within the butanone again, what we will see is we've got 3 distinctly different types of hydrogens. So if I highlight them, group 1 over here. Now one could argue that the CH3 group here is actually the same as the CH3 group here. But in terms of NMR, they're quite different. And the reason for that is this CH3 group is next to a C double bond O. But this CH3 group is next to a CH2. So therefore this CH3 or methyl group is not the same as this. And equally, this set of 2 hydrogens is unique because it's the only CH2 group there. And on the one side you have a CH3, the other side have a C double bond O. So in this case we have 3 different environments and we have 3 different sets of peaks. Let's look at environments in a bit more detail. Sometimes you'll refer, or you'll see in a textbook, that the environments are referred to as equivalent hydrogens. And then later on I'll be talking about the height and the width of the peak being proportional to how many hydrogens a molecule is represented by. But before we do that, I would like to look at different molecules. And I've listed quite a few different molecules over here. What I would like to talk about first of all is the different environments again that exist within molecule. Let's start with, in this particular case, I'm going to say that this CH3 group is the same as the CH3 group. And the reason for that is the CH3 group has a neighbor which is CH2, and this CH3 group also has a neighbor which is CH2. So both CH3s have the same neighbor, and therefore they are exactly the same. And the CH2 group again, is different because it has CH3 on either end. Bottom line is the CH2 is not the same as the CH3. Okay, now let's move on to the second molecule. This time round, this CH3 over here is not the same as the CH3 on the other end. So what I'm saying now is this CH3 is distinctly different to this CH3 over here. And the reason for that is the CH3 over here is next to a CH, but this CH3 is next to a CH2. So both CH3s in this particular case are quite different. Okay, and the other molecule bits now, or the components, this CH2 is quite unique. It's the only CH2 there. And lastly, the CH is obviously very different because it's the only one that exists. Now equally, I could work through all of these and we could label the similar groups and the different groups, but to save time, I'm simply going to give you the answers for all these. And what you will see is the similar and different types of groups. So just quickly running through this again. We have two CH3s the same because they're equal distance apart from the CH2. This CH3 is different from that CH3 as the neighbor here is CH, but the neighbor here is CH2. So they are different. This CH3 is different to this CH3 because we have CH neighbor here, but a CH2 neighbor over here. And equally, these two CH2s are not the same because the neighbor here is CH3, whereas the neighbor here is CH. In the last molecule that I've drawn over here, these two CH3s are the same, and the reason for that is they are both the same distance apart from the OH group over here. And then lastly, the two CH2 groups, sorry, the CH2 and the CH3 are distinct because they don't have any similar parts within the molecule. Now, I want to pause over here to ask if anybody has any questions regarding the different environments that I'm talked about. And once we've established the fact that we are relatively clear on the environments, we can then talk about how the environments correspond to the number of different signals that we have in the NMR spectrum. So if anybody has any questions, please fire them through annotate now while I pause and wait for you. Okay, I don't seem to be getting any questions, so I'm assuming the basic understanding is there. Okay, in that case, I'm going to move on now. And we've got different molecules which I've listed over here. Ideally, you want to be working through these in your own time. But for now, let's just work through them one at a time. Okay, let's look at this molecule. I've listed the fact that I've got two different signals, and again, I hope you can appreciate that this CH3 is exactly the same as this CH3, not only because it's two CH3s, but for the reason that this CH3 and this CH3 are on the same carbon, and they are both equal distance apart from the CH2 over here. So we've got two different CH3s, but for NMR purposes, they are exactly the same because they have the same distance away from the CH2. So we would have two signals, one signal for both of these, but because these are exactly the same, they will only have one signal. This CH2 is different, and therefore it's going to have another signal. So the two signals we're talking about are one for this CH2 and one for this CH3. Now, a few slides ago, I talked about the fact that the signal that we're going to get is corresponding to how many different environments. So again, we've got one environment here and another environment here, which explains the two signals. And then let's try and explain this ratio over here. Now, the ratio is referring to how many hydrogens we got altogether. So if we count up the hydrogens, we got 3 hydrogens here, 3 hydrogens here, that's 6, plus the 2 hydrogens here, which are 8. The ratio here, can you see, 6 plus 2 is going to be 8. So the two signals that we're going to get, one of the signals is going to represent these 6 hydrogens, and the other signal is going to represent the 2 hydrogens over here. So let's move that forward and look at another one now. In this particular case, we've got 3 different environments. This one is different to that one, which is different to that one. How many hydrogens do we have? 2 hydrogens here, plus the 1 is 3, plus another 3 is 6. The ratio is 2, which is that one. 1 hydrogen is that one, and the 3 hydrogens are that over there. Let me just highlight them in. So the CH2 here is this one. The CH3 over here is the 3 hydrogens here. And last of all, the single hydrogen here is responsible for that one over there. Let's keep going. Last one over here, again, let's just remind ourselves, because this CH3 and this CH3 are exactly the same distance apart from this CH over here, they're both exactly the same, they will only give one signal. This hydrogen in the center is distinctly different, so this will give its own particular peak. Now, the ratio of 6 and 1 comes from this 6 over here is again responsible for the CH3 here and the CH3 over here. And the 1 in the ratio over here is this one over here. So that explains to some extent how many signals we get and what the height of each particular signal represents. Again, the height of each particular signal represents how many hydrogens are present for that particular peak. Okay, I'm going to swiftly move through now. I don't want to work through every single example. I'm sure you can do that in your own time. What I would like to do now is focus on how the actual spectrum looks like. So probably for that reason, I'm going to go back to the butanone example, which is this over here. Now, what we have to establish is which one of these peaks over here is responsible for the signals that have been generated over here. Now, I hope what you can see is that this particular line over here is similar in height, at least, to this particular line over here. Now, the lines that you see which I've just drawn, they are known as integration. Okay. Now, if I was to take a ruler and I measured the height of this line and I measured the height of this line over here and compared it to the line over here, without even actually taking a ruler, I think you can appreciate that the line here has got the same height as the line here, and both these lines are actually higher than this line over here. And if I was to work out the ratio of this line to this line to this line, the ratio, I know for a fact, would work out to be 3 to 3 to 2. And what does that mean? Well, the 3 represents 3 hydrogens here, 3 hydrogens here, and 2 hydrogens over here. So just by looking at the height of this line, I know how many hydrogens that is responsible for. Now, how do these lines originate, or where do I get them from? Well, the computer that actually does the calculations is measuring the area underneath each of these peaks. So if the computer measures the area underneath these peaks, it translates into a line here. It measures the area underneath that, recalculates it as a line here. Similarly, it calculates the area underneath this set of peaks, and it gives it a line over here. And then by simple ratio, I can see that it's 3 to 3 to 2. So straight away, I know that this peak over here and this peak over here are responsible for the CH3 here and CH3 over here. Right now, I'm not sure what's the order. I don't know if this peak is for that, and I don't know if this peak is for that. The only thing I know with absolute certainty is that this CH2 over here is this over here. So if I color that in exactly the same color. So I know this one over here is that one over there. What we need to do now is try to figure out whether this one is that or this one is actually that. So for simplicity, to make things clear, I'm going to erase the highlighting here, and we're going to start from scratch to figure out which is which. Now, luckily for us, there is a simple way of figuring out whether it's this or this peak, which is actually responsible for this over here. Now, let's make this particular part of the molecule our focus in terms of determining which peak is which over here. Now, it's always going to be the case that if I have something electronegative such as oxygen, now the electronegative element, in this case oxygen, if you have a group next to it, that group is always going to appear away from zero. So if you talk about the scale starting over here at 0, because this CH3 is closer to the C double bond O, that's the one that's furthest going to be away from the 0. So I can very easily figure out now that this CH3, the purple one, is actually this one over here. And the reason for that again is because the CH3 is closer to the C double bond O, therefore it's furthest away from 0. And comparing these two, this is the one which is furthest away from 0. And now my job is pretty easy. The CH3 here, which is the furthest away from the C double bond O, is going to be closest to the 0. So the green ones are, this one over here is going to be this over here. Now again, I'm going to pause for a few seconds to give an opportunity for anybody to ask any questions with regards to whether there is any confusion about how to understand which peak appears for which type of hydrogens. In fact, what I'll do even better than that, I'm going to throw open to you. Actually, no, I'll just wait for any questions if anybody has any. So please fire in the questions if you have any. Okay, that seems okay. Nobody has any questions. Okay, in that case, what I will now try to do is explain why we have a situation in which this particular peak, which I refer to as a peak, has actually split itself into a set of 4 smaller peaks. This one over here has not split into any smaller number of peaks, whereas this one over here has again split into a smaller set of 3 peaks. Now this is the actual part that most students find the most difficult, because, well, explaining it is not quite easy, and it does take a significant amount of time to train your brain into figuring out exactly why the peaks have split up into smaller bits. Okay, first of all, let's explain the easy bit. Now, the easy bit to explain is the one that hasn't split up into any smaller pieces. Okay, the thing that is very different about this CH3 compared to this over here is, again, something to do with its neighbor. Now, the CH3 neighbor over here is a C double bond O. Now, in fact, I'm going to open this question to people. Can anybody tell me what is different about this CH3 compared to the CH2 here and CH3 over here? And again, I'm going to wait for somebody to try and give me a response as to what is unique about this CH3 compared to the other. So over to you guys. If you have an answer, please send it through. Anybody? Okay, let me give you the answer as nobody has come up with an answer. The thing which is unique about the CH3 here, let me just get that back. So the thing that is unique about this particular CH3 group compared to the other CHs is next to this CH3, I do not have a carbon which has any hydrogens onto it. Okay, so the CH3 over here, Badullah is kind of got the answer. The CH3 over here is next to a C double bond O, but this carbon has hydrogens next to it. Now, if we look at the other two, the CH2 over here is got next to a carbon with hydrogens on it. Same thing over here, this CH3 over here has got a carbon with hydrogens next to it. I'm just going to check. Now, what we say in NMR speak is that there is no carbon with hydrogens on which can split this particular signal. So you can see this signal remains unsplit. It's just a normal single peak and it stays a single peak because nothing next to it or the neighbor next to it can't interfere, and neighbors can only interfere if they've got hydrogens on there. So there's no hydrogens over here, so it can't interfere with this over here. Over here, the difference is because this has hydrogens and this has hydrogens, these hydrogens will interfere with this hydrogen pair, and these hydrogens here will interfere with that. And we, as chemists or analytical chemists in this particular case, must be able to predict whether we have splitting, as in the case over here and here, or whether we don't have splitting in the case of this CH3 over here. Now let's try and explain the splitting part. So what we have is, let's talk about this one over here. This is a CH2 group, and we've already established because it's two hydrogens, and this is a shorter peak, so it's two hydrogens over here, that this signal corresponds to that. What we need to explain is, how do we get this splitting into four? And that splitting into four is actually a quartet. Now, looking at the quartet, the signal over here is being generated by these CH2s. The splitting that we are observing is CH2. I'll say that again. The CH2 signal is that, but the splitting is because of the neighbor. Now, neighbors of this CH2 are free hydrogens. And whatever the number of hydrogens are in the neighbor, what we do is add one to it. So next to this CH2, there are free hydrogens. If we add one to that, we end up with 4. And can you see that's exactly the number of splits that we have over here? And that particular rule is known as the n+1 rule. And what that means is you look at the neighbors, you add 1 to it, and that will give you the number of splits. Now if we look at this one, the green hydrogens are this over here. So the green hydrogens, if they are this over here, that's the signal. But next to the green hydrogens, we look at the neighbors now. Now, how many hydrogens are the neighbors? The hydrogens which are the neighbors are actually free. Sorry, wrong way around. So let's start again. We've got 3 hydrogens here. Next to them, there's 2. And 2 plus 1 will give you the 3 over here. So what we have is a splitting of 3, which is known as a triplet. And the reason why we have 3 again, 2 plus the 1 is a 3, so we have a triplet. Again, I'm going to pause for a few seconds to give an opportunity for anybody to ask any questions here regarding splitting. Okay, again, there doesn't seem to be questions. What I'm going to do finally now is to give you the hands up function so you can give me your traffic light version as to how good or bad you think your understanding is regarding the NMR topic. Okay, what I'm trying to do now is go through your questions one by one. Somebody asked me the question, does this only work for CH bonds? There's two different types of NMR. One, well, the two different types of NMR are proton or hydrogen NMR, which is the one that I've talked about today, NMR, which is actually a lot simpler than this particular one, but I decided to choose with the hard one because we know the hard one. But does the splitting rule only apply to CH bonds? Yes, the splitting rule only applies to CH. For example, this CO, it doesn't even have a signal. And the reason why it doesn't have a signal is because it doesn't have any hydrogens. So if there's no hydrogens, they cannot cause splitting to their neighbors. I hope that explains that one. Does the number of peaks only tell us the number of hydrogens? Environment, then peak that I have over here. The height of the peaks or the integration of the peak area environment. So in regions in that environment, which is true here. In this, few more. So two groups are in the same material. They're the same groups, but they don't have the same neighbors. This has a C double bond O neighbor. This is a CH2 neighbor. So therefore, this set of hydrogens is different to this set of hydrogens. However, I had a different molecule, and let me two CH3s at the end now would be exactly the same because they have the same neighbor next to them, and the neighbor that I'm talking about is having a C double bond O. Okay, if there are no further questions, then I believe we can call it a day here. I'll stay online for a few more minutes in case anybody fires a question through. If there are difficulties in accessing annotates for the questions, I don't mind receiving them through Remind. Okay, in that case, I think I will terminate the session here. Thank you for your time, everybody, and as usual, if there are any questions, please feel free to fire them across. Thank you, and have a good night. Bye.